You're on. Great, thanks. Well, good afternoon. My name is Tracy Kreckman, and I work for a company called CYMER, which is an ASML company. And I'll explain a little bit more about what we do very shortly. So, how many of you are familiar with the old Jetsons cartoon show? So, I was surprised as I was doing some research to find out the Jetsons first aired way back in the early 60s. And it's interesting to see how the predictions of the future that they were making back then have come true today, and what that means for us in our environment and our role as instructional designers. Because as I tell my students in our classes that I teach, we're living in the future. So what we'll talk about is the characteristics of the learners in this technological age, and also how we apply some of the timeless truths of instructional design to those learners. I'll give you some examples within our business. So I was going to show a little promotional video, but I think instead I can do a better job myself of explaining exactly what we do. So making a chip, making a microchip, is very similar to making a print in a darkroom using an enlarger. With an enlarger, you have a light source that shines through a negative onto a piece of photographic paper. You then process that paper, and there's your image. Making a microchip is very similar. We use a specialized form of light, we shine it through a circuit pattern, and then we project that circuit pattern onto a wafer, except we shrink it down instead of enlarge it. And so we create maybe 100 different patterns of that circuit on the wafer. And then we process it. Except we don't stop there like a print. We're going to add more chemicals, expose it again, process again, and do this over and over and over to build up successive layers, because we're printing our circuit patterns in 3D. And sometimes it may take an entire month for a wafer to go from start to finish, from first coating to being cut up and packaged. And so our role is to create the tools that perform that function. So our office here in San Diego, ASML is a Dutch company, and we merged about 5 or so years ago, and we started out as CYMER. CYMER is the light source side of that process, and now ASML handles everything else. They have this big machine called a scanner, and that's what handles the wafers and actually performs the process. So we create the tools that folks like Intel and Samsung and others use to make microchips with. So in your phones, in your tablets, in your laptops, odds are very good that a number of the chips in there were made using our tools. So it's been very rewarding work knowing that we are helping out your everyday life in the way that you do your work, you socialize, and so forth, being able to create chips that are more powerful, more cost efficient, use less battery power, so you can do more and more with each successive generation of tools. So just taking a quick look at the predictions of the future over 55 years ago. Taking a look at what they were predicting back then. Big screen TVs. Video conferencing. Now we are communicating with people all over the country, in fact, all over the world we need. Robots to do our housework. Anybody have a Roomba? What about flying cars? That's the one question everyone seems to keep asking. Where's my flying car? Yeah. Yeah. They're working on it. We got some prototypes, playing around with it. So a lot of the things that they predicted have come true, maybe not as fast as we thought or to quite the same extent as we thought, but the technology continues to move forward. There is something, has anyone ever heard of something called Moore's Law? Moore's Law was a term coined by Gordon Moore, a co-founder of Intel. And it started out as an observation, saying that our chips essentially become twice as powerful every 18 to 24 months. And that observation held true far beyond what he expected it would, to the point where now, instead of simply being an observation, that has become an industry driver. The chip manufacturers schedule their next shrink, as they call it, the next stage into smaller chips by that schedule. It's starting to slow down because we've sort of run out of our bag of tricks that we can use to shrink things down. That brings us to our next level of technology that I work on myself. So what are the characteristics of the learners that we are now dealing with in a high-tech company like this? So all of this provides context for our business, a high-tech industry, where we have a unique set of learners, I think, with characteristics that don't quite line up with the bell curve of most other kinds of learners. One, we have learners that are more geographically diverse. And folks in the LDT program understand this because it's an online program. Folks are located all over the place. You don't have to be centered in a single location to be able to learn. In our example, in our field, we have folks that are literally all over the world because we have fabrication plants, not only in the US on both coasts, but also Taiwan, Korea, Europe, and so we're working really round the clock in communicating and dealing with issues worldwide. So how do we train people who are geographically diverse? Well, these are the same sorts of solutions that we use in our LDT program. Synchronous distance learning, where we have audio and video conferencing, instant messaging, everyone's kind of coming together virtually at the same time. Also, our asynchronous distance learning tools, recorded videos, podcasts, CBTs, wikis, and so forth. So we've got tools that we're familiar with. But just because we can do something with these tools doesn't always mean that we should. Because sometimes we, I think, get into a mindset that we must use the latest and greatest technology to be able to communicate across these vast distances as efficiently as we possibly can. But sometimes old-fashioned travel is the answer. An example, last year we rolled out a new generation of our system, and we could have provided training online at a distance. But we found that there was value in sending someone around to those sites to have face-to-face contact, because those people at those sites felt more valued, that someone would take the time to go out and be able to interact with them in person. And sometimes conveying that value is more important than the money that we can save by hosting all of this online. I put in, I logged about 60,000 miles last year, traveling around to different sites. And I think not only I got more out of it, but my learners got more out of it. Simply being able to communicate and build relationships that they can contact me at any time. They know who I am. You know, we've had lunch together and so forth, and that kind of thing has some value. And so we want to balance out the use of our technology with more conventional methods of training, looking at some of the non-tangibles as well. Also, our learners are very diverse culturally and linguistically, much like we have in the LDT program. I was just thinking about all the different languages that I hear around the office on a daily basis. Just here in the San Diego office, in addition to English, I hear Dutch, Mandarin Chinese, Korean, Hindi, Spanish, Russian, even Japanese. So we have a very diverse group of learners because they are working all over the world. So you need to know your cultural mores. Know what are the cultural norms. You don't want to offend people. And one of the things that I learned fairly early on, a lot of my students come from Taiwan and Korea, and a simple thing, doing an introduction with a business card. For us in America, we just take a business card, oh, here you go. Whereas for them, the polite thing is they hand you their business card with both hands, with a slight bow, and that's how you are supposed to receive it as well. Just knowing little things like that goes a long way to building those relationships with your students, that you don't want to give the impression of being the ignorant, ugly American. You want to be able to relate to their culture as well. Also, keep your vocabulary continuously in mind, not just as you're creating your training materials, but if you're doing instructor-led training. If you need to use a word that the learner may not know, make sure to define it. For example, one of the software modules that we use on our system is called an HSM. It stands for Hierarchical State Machine. I'm not expecting one of these students to have ever heard the word hierarchical in their vocabulary class. Most English speakers probably aren't familiar with the word, but just meaning having to do with an organizational structure. And so when you want to keep in mind words that your audience may or may not know, that helps out to be able to define those words so that everybody's on the same page and they understand what you're talking about. Also, even though we are in a high-tech industry, there's a big difference in technical literacy. Most of the students that I have are very technically oriented, but we do have folks working in other areas, such as planning upgrades in the field, or change management folks. Their day-to-day role may not be using this high technology, but they come into our classes to be able to learn the context of their own work. And we have to adapt to just about any level of technical literacy. So we don't want to assume that our learners are technically adept. Most are, but not all. So if necessary, we create job aids, coaching tools, wikis, things like that. We've created a variety of tools as online resources for people to perform different aspects of their work. For example, we use what's called Team Center that contains engineering documents that list requirements of the equipment that we are producing. We have our service knowledge base for the field service engineers to access PowerPoints and just-in-time learning assets. We have a product called Coach that lists all the service procedures so they can follow these procedures step by step as they're performing service functions on the machines in the lab. So we use all kinds of different tools for different job roles. We also want to characterize the knowledge of technical subjects. And I'm going to steal from Ruth Clark. We find that for the work that we do, Ruth Clark's book on technical training is very valuable, where she breaks down the different kinds of knowledge into these 5 categories: facts, concepts, processes, procedures, and principles. We find that each of those different types of knowledge are best taught in different ways. So it's not a one-size-fits-all. I'm going to use this particular tool to teach everything. So what are some of the timeless tools of instructional design that we can apply? And I'm going to couch this and say, at least within my context of training high-tech employees, I found these things to be particularly valuable. So this comes from the basic 540 course. So these may not be new to you, but I'm just showing how we find them particularly useful within our field. So our performance barriers. Anyone know what the kind of our classic performance barriers are? Remember your 540? Things like skills, knowledge. Yeah. Skills, knowledge, that's the knee-jerk reaction. If someone is not performing the way you think they should, and this applies all the way from an individual level all the way on up to an enterprise level. If someone isn't performing the way you think they should, the knee-jerk reaction is they don't know how to do it, they need to be trained. So the test is to say, well, if you were to hold a proverbial gun to their head, would they be able to do it? If they can do it, then it's not a skills knowledge issue. If it is, then we move on to do training needs assessments and things like that. But if they know how to do it, skills knowledge is not the issue. Another one is motivation. And so Sean, they talked about this this morning with the Keller ARCS model. More simplified breakdown of motivation is value and confidence. Do they see the value in what they're doing? Do they have the confidence in themselves to be able to do it correctly? If you're unsure of yourself, like, I'm not too motivated to do that. Other things are incentive. Are people being rewarded for doing the right things? Classic case is a call center where people are being rewarded for the number of calls they're handling. Well, the unintended consequences is they're going to try to shorten each call and perhaps provide inferior quality of service in order to increase the quantity, because that's what they're being rewarded for. We want to make sure we are providing proper incentive to folks. Lastly is environment. Is it too hot, too cold, too noisy to do your job? Do you have all the right tools? Do you have the right software? So we kind of break these down into internal and external categories. So the skills, knowledge, and motivation, that kind of comes from within. Whereas the incentive and the environment may not be under our control. Those kinds of issues we may need to forward to managers who can do something about policy regarding incentive, or others who can okay a purchase to make sure you've got the tools that you need to do your job properly. Find that these are some of the classic barriers to performance, and this is extremely useful to get at the root issue. Whenever you find a barrier to performance, say, well, how do we categorize these? And I'll give you an example in our field. One of the key pieces of equipment in our system is called a droplet generator. Now, the way that we make light on our newest system is called an extreme ultraviolet light, or EUV. And the light that we create in order to make these very small sizes on the chip it's like Star Wars. This wavelength is close to the X-ray range, and the way we create it is to melt highly purified tin to it, and so it's a liquid. Then we propel it with about 3,000 pounds per square inch of pressure, 200 atmospheres of pressure. And we squeeze it through a tiny nozzle, almost like an inkjet printer. And then we squeeze the nozzle. And so it is very similar to an inkjet printer, except we're shooting this tin 3-4 feet across our vessel. And then inside that vessel, which is under vacuum, because all the EUV light would be soaked up by any air, we squirt 50,000 droplets of tin every second across the vessel. Then when it gets to the middle, we've got this high-powered laser that's focused down to a pinpoint that we blast the tin droplet, turn it into a plasma, and blow the droplet into oblivion. But that process creates the specialized light at 13.5 nanometers, this EUV light that we need, that then gets focused into the scanner where it can be directed to the chip. And if it sounds just absolutely nuts, it is, but it's the only way it can be done that people that we've experimented with so far. But this droplet generator is a key piece, and we have to replace these on a pretty regular basis because they run out of tin. They only last for so long. So we either have to reload them, or once the performance degrades, we have to replace them every few days. We reload maybe every 6 or 7 days, and then we might have to replace them once a month or so. So where we want to speed up the process of replacing these droplet generators, we kind of take a look at this and say, time is money. How can we speed up this process? What are the barriers to be able to swap these things out in the amount of time that we want? Well, skills and knowledge. Do our field service engineers know how to swap them out? Are they motivated to work as quickly as possible? Have to get across the value. Making wafers is almost like printing money because of the revenue that's generated by every single chip that we produce. We want to be producing 100 wafers an hour and 100 chips on each wafer. And if our system is down for 5 hours, that's a whole lot of money that's being lost. So we want to convey the value of doing the job as quickly and safely as possible. So that kind of ties into an incentive as well. On the environment side, do they have the right tools to be able to do this job quickly and efficiently? So these kinds of questions help us narrow down the real core issues in terms of how can we make our processes more efficient and thus more profitable. Other things, learning objectives. So probably all know kind of the classic elements of a good learning objective. This is something we find extremely valuable. It's amazing how often you see bad learning objectives written by engineers in their draft PowerPoints. I got to go with Robert Mager, and we want our objectives to be observable. For example, how many times have you seen objectives like, the objective is to learn this, it's to understand that. Now we want something that we can see. Want to use what I remember back from 540 is the hey dad rule. Should be able to fill in the blank. Hey dad, watch me do this. Watch me describe this. Watch me explain this. Watch me list this. You can't say, hey dad, watch me understand this. So from this, we've kind of developed the ABCDs of a good learning objective. Our audience, behavior, condition, and degree. So here's an example in the process of replacing a droplet generator. Our audience is our field service engineer. The behavior is to replace the droplet generator. The conditions. What are the constraints? Say within 5 hours, a degree. How well does it need to be done? Because the process of replacing a droplet generator is going to break and reestablish a seal in a vacuum environment. We have to make sure that we have no leaks. So our learning objective becomes the FSE, field service engineer, will be able to replace a droplet generator within 5 hours with no leaks on the system. And that becomes something that we can observe, we can measure, that leads to better performance. So some of the last things, adapt to your learners. I've talked about this already because your learners are so diverse in terms of their background, their education, their technical proficiency. We allow extra time, for example, when we have a class full of students from Taiwan or Korea, because obviously I need to speak more slowly, maybe repeat things, rephrase things, take all those into account. Adapt to your tools. Things don't always work the way they're supposed to. When I've been in the lab, where's the tool to drain the water system? Oh, I can't find it anywhere. Oh, boy, okay, we got to make something up to make this work. In a high-tech environment, you're talking about bleeding edge stuff. Things don't always work the way you expect they're going to. Finally, adapt to your environment, because things may happen that are out of your control that you have to flex. Last week, for example, I had a lab session where we were scheduled to be on the machine from 7 a.m. to 7 p.m. to train. And our engineer said, well, we really need to run some important software tests on the machine. Could you reschedule your training to go at night instead? Oh boy, confer with the students. Is that going to interfere with your travel plans? No. Okay, we can do that. And so instead of training during the daytime, our training session went from 7 at night until about 3 in the morning. And we realized, yeah, it's not the way we planned it, but we got it done. Students learned. We account for it in terms of taking some extra breaks, making sure everyone has sufficient caffeine, that we go a little bit more slowly to make sure we are doing everything as safely as possible. So, in a nutshell, Semper Gumby, always flexible. I'm actually running a couple minutes over. Any quick questions? All right. Thank you very much for your time.